Okay, since we have a lot to cover today, I'd like to start today's webinar. So welcome everyone to KiboCUBE Academy Online. This is our first KiboCUBE Academy webinar series of 2023, and we're really excited to have you here. So before we begin, I'd like to mention a few things. For this webinar, we are using Zoom, so please use the Q&A box to ask questions. Please do not write in the chat. Please do not direct your questions directly to the speakers. Please write in the Q&A box so that we can open them for everyone to see. Second, please answer our questionnaire that we will be putting in the chat box later on. So the chat box will be used for us to send you information, useful links to the questionnaire and all that. So please answer our questionnaire before you leave. We would really like to hear your feedback on the different webinars we do, especially KiboCUBE Academy. Yeah, so please let us know your opinion. And last but not least, if you are on social media, please use the hashtag Access to Space for All, KiboCUBE Academy to help us promote this webinar. We are active on Twitter, Facebook, LinkedIn, and Instagram at UNOOSA. So today's agenda will look like this. We will start off with CubeSat mission assurance and then go into the satellite facility tour of Kyutech. The CubeSat mission assurance part will be a bit longer, so we'll take about 80 minutes, and then we'll have a Q&A after that, and then we'll move on to the satellite facility tour of Kyutech, and then, of course, have Q&A after that. Today's speaker is Dr. Mengu Cho. He is the professor at the Laboratory of Lean Satellite Enterprises and In-Orbit Experiments at the Kyushu Institute of Technology. And of course, he is part of UNISEC. I will introduce him later. As I have just one more slide that I'd like to mention. Of course, it's about KiboCUBE Academy. All of you are here, so I bet you understand what we're doing here, but really just to explain again, KiboCUBE Academy aims to provide theoretical knowledge to develop, operate, and utilize small satellites. So we're really covering the whole life cycle of satellite development. Just to mention the old webinars we were doing, so in season 1, we conducted 4 webinars in January, February 2021. You can still see the recordings on our website. And season 2 has started from November 2021. We have 21 pre-recorded videos up on the website, and you can see the list of the whole thing on the right-hand side of this slide. There's one webinar that one recording that we haven't been able to upload yet, but besides that, we have everything on the website. Please take a look. They're all nice short webinars that you can get all the information on, and of course the PDF presentation is along with that on our website, so please have a look. Last year we actually did KiboCUBE Academy for the first time hybrid in Tunisia, so we also have that recording and the presentations there. So yeah, anything about KiboCUBE Academy, it's all on our website. I believe my colleague Wenbin will be putting the link up in the chat. But yeah, if you have any topics that you would like us to cover in future KiboCUBE Academy sessions, please let us know, and you can drop that in the Q&A, or maybe you can answer the questionnaire and let us know there. I'll go back to introducing Dr. Mengu Cho, and I'll give him the floor.
Okay, good. Okay, now today I'd like to talk about the 2 things. One is this CubeSat mission assurance, and another one I'll take you to some virtual tour of our facilities. Yes. Okay, first let me introduce myself. Some of you know me because I see some name of my former student in the participant list. But I've been the professor at Kyushu Institute of Technology since 2004. I joined this university Kyutech. We call it Kyutech in short in 1996. Yes, and I also do the visiting the faculties at NTU Singapore, also Chiba Tech in Japan. So I'm also a coordinator of United Nations Japan Long-Term Fellowship Programs, postgraduate study on nanofabrication technology, PhD. Yes, and I do work on lean satellite, spacecraft environment interactions. These photos are the satellite I was involved in Kyutech. So Kyutech is located here, 1,000 kilometers west from Tokyo. And if you look at from space, we are here. And we are actually closer to the to Korea rather than to the Tokyo. Yes. So we are national universities founded in 1909 with a history of more than 110 years. And this is only one remaining from 110 years ago. Yes, at the front gate. Yes. So at the Kyutech, we have this Center for Non-Satellite Testings, which can offer all kinds of testings for satellite up to 50 centimeter, 50 kilograms. So we tested more than 70 satellites since its inauguration in 2010. Well, I will take you to a tour later. So I'll explain more. So these are the satellites we have launched since 2012. And we are the number one academic small satellite operators according to this Bright Space Tech Report. So today's my talk is based on my experience of working these many satellite projects and also some collaborative work among the academic members of UNISEC. So first, let me introduce this UNISEC activities about mission assurance. So UNISEC Japan's, I think many of you know already, it's a universities space engineering consortiums. It consists of 36 universities, and we have 260 individual members. Many of them are the people who are working in universities. And we maintain a cooperative relationship to conduct practical space development and utilizations. Since 2003, it's already 20 years ago, the first CubeSat was launched. These two CubeSat, Sci4, Qt1, is really the first CubeSat launched into space. And amazingly, Sci4 is still working. Since then, Japanese universities launched so many satellites. And through these activities, we have learned lots of lessons. Yes. And today's talk is based on those lessons we have learned. So in 2020, yes, everybody understands that we were in pandemic, and we became suddenly, free, or actually confined to house. Couldn't go anywhere. Usually, professors like to go travels to attend a conference, to meet the people, to do lectures, but we are suddenly grounded. And so we discussed, is there any way to use this free time, which suddenly appeared in a more effectively, rather than, just sitting in house and reading books and going through internet. So we discussed and decided to have some kind of sessions on lessons learned from university satellite project in a UNISEC. Because we have so many university projects, some of them had a really good the result. We were really successful, and some of satellite failed completely. So through those experience, we thought maybe it is a good time. And now we, using this free time, go back to our project and discuss each other's what really went wrong, what lessons we have learned, and what to do to not to make a same mistake again. Well, we found very good sessions. I think about 20 projects presented. Each time maybe 3 hours. Yes, and we talked really honestly what really went, and very good discussions. And we did this survey on lessons learned for the mission success, and we made this 439 pages of report. And we analyzed success and failure. And we also extracted requirement for mission assurance of micro nano satellite. Unfortunately, this report is in Japanese, but you can download freely, and using the computer, you can do machine translation. So following that activity in 2021, 2 years ago, we worked on a mission assurance handbook for university-based LEO satellite. We did further analysis of the failure cause by doing very intensive interviews with the persons in charge of the project. And based on those root cause analysis and adding some more the new findings, and we published this mission assurance handbook for the university-built LEO satellite in March 2022. And today's lecture is based on this mission assurance handbook. I'll later show you the link to download this one. So please have your smartphone ready. So first, let me talk about this lessons learned. Well, actually, I made this lecture on lessons learned, and it is lecture number 21. The lessons learned from CubeSat missions. It's a KiboCUBE Academy on-demand version. So if you check this QR code, yes, you can get this recording. So please watch this one later because I discuss those lessons more in details. Yes, and I made about 10 satellites. I talked about this 10 satellites. 3 of them are not really CubeSat, but they were university satellites. And so yeah, I analyze, I present what went wrong and also the root causes. Or, for example, for one 3U CubeSat, it was very difficult to assemble. And every time they assembled, it took so much time. And that suppressed the time for the system test. And 1U CubeSat, because it was a very fast satellite, and the schedule management was very poor. And 2U CubeSat, they had difficulties in satellite communication because the satellite was built by students from mechanical engineering students. And 50 kg satellite, that was the first satellite built by that group. And it had a frequent power reset, erasing attitude control history, and so the operation was very difficult. And another 50 kg satellite, they didn't know about much about the power systems. And the 7 kilogram satellite, actually this is my satellite, that was my first satellite. The optimistic, very optimistic confidence, baseless confidence, without any basis in design, without verifications, yes. And 1U CubeSat, we made a mistake to make a design requirement, which was not consistent with the mission requirement. And another 1U CubeSat, internal noise prevented uplink success. And those kind of lessons are written, discussed. And so you can look at. And in this lecture, I also talked some part of the mission assurance handbook, but today I'll go more deeper into the mission assurance aspect. So for those lessons learned, I interviewed the key person of each satellite project to analyze the root causes. And we found many common causes among different cases. Poor schedule management, this was especially true for the first satellite. And team structures, and inconsistency in requirements, and improper verification plannings, and wrong strategies to avoid total satellite loss, and insufficient full system end-to-end test, and difficulties in assembly, integration testings, and poor understandings of the rationale behind designs. And so, based on those analysis, we made mission assurance handbook. So for the mission assurance, what is a mission assurance? Mission assurance is a series of activities Mission assurance is a series of activities to identify factors in design, making, operation of satellite that will hinder mission success and to eliminate, to decrease the effect of such factors. So to improve the success rate of as much as possible. Also, we should consider university satellite as lean satellite. Lean satellite is a wording I often use to describe the CubeSat and many of nanosatellite, microsatellite. But to describe those satellites not by the size or masses, but by the philosophy. So lean satellite is a satellite utilizes non-traditional risk-taking development and management approaches to provide satellite value to customers and or stakeholders at low cost and with short time to realize the satellite mission. So lean satellite tolerates a risk. Yes, when you build a CubeSat, yes, we tolerate a risk. Otherwise, CubeSat takes too long or too expensive. So we have to, at some point, we have to make a compromise for the reliabilities against cost and schedules. However, but we still need to achieve mission success as much as possible. So we are not saying failure is not an option, but at the same time, we are not saying failure is accepted. So we have to set certain level of the mission success. For this mission assurance handbook for university-built lean satellite, we target satellite project at universities and polytech college in Japan. Not only for the first project, but also the second or later project. Because even the second, third satellite, we still make a mistake. So summary of points to be kept in mind of faculty members and students to improve the success rate. So I really want the faculty member to read this one because it was written from the faculty like me. And so I really want to say things to those the professors. And it was organized in order of project life cycles, and it's published and available online. And many of the content is still applicable to satellite project in new space companies or non-Japanese organizations. It doesn't have to be Japanese universities. There are points which is unique to the Japanese satellite project, but there are many things are common. So we made an English version. So you can use your smartphones and capture the QR code below, and it's free of charge. You can download this one. Okay. There are some 3 persons raising hand. Do I answer the question now?
No, we'll take all the questions at the end.
At the end.
If you have any questions, please put them in the Q&A. And yeah, we have also shared this link in the chat box, so please take a look if you weren't able to take a proper picture or scan the code.
Okay. So I give 1 minute for you guys to take up the picture of this QR code. Okay. All right. So the contents is made by 10 chapters. Yes, introductions. And from the chapter 2, project management, and to the post operations, it's ordered according to the project life cycle. And at the end, we write about the sustainability of university satellite programs because it is also very important. Yes. It shouldn't be one shot project. Yes, it should be sustainable. So from now on, those page title numbers, this number, like this, right now it's 3.3. I changed to the one used for the handbook. Okay, so now the next page becomes the 2.1 from 3.3 because 2.1 is the chapter number in a handbook. Okay. So the project management. Okay. The schedule management is really important. So first project often fails. Most likely, it's a root cause is improper schedule management because it's the first time for them to do satellite project. So they do not know how to allocate schedules. Usually, they are optimistic. I have never seen a pessimistic schedules. Usually, schedule is always optimistic. And they spend very little time in system test. So the handbook write about the guideline for the project milestones until satellite delivery. So after you define the mission, most of the time we do something called the mission definition review. From those mission definition reviews, they goes to the PDR. So from PDR, it's D minus 13 months. D is a satellite delivery. So from PDR to satellite delivery, 13 months or longer. Okay. If you try to squeeze less than 13 months, if it is a first satellite project, it's extremely difficult to finish. Or if you are very experienced team, you may shorten this 13 months. But many times, I think 13 months is probably shortest ones. Yes, considering also all kinds of procurement of component and the frequency licensing and also safety review and also those kinds of things. And at D minus 13 months, you finish proof of concept, confirm that the missions are feasible, and you finish most of engineering model designs and start procurement. At that time, you usually have the PDR. So before PDR, you need to verify that mission is doable using hardware such as breadboard models. And if their feasibility is uncertain, you may want to give up missions. Yes, because you shouldn't think that, perhaps it is okay, or we can work on the EM stages. It's very risky. Yes. So if you have multiple missions and the missions you cannot prove that you can do by this time, you may want to drop that one. So from PDR, first 3 months, from D minus 30 months to D minus 10 months, so you have first 3 months. So you need to wait for the EM hardware delivery. Yes, it takes time to get a product, especially now, especially during the pandemic, it was extremely hard to get a component or even simple, very simple electronics parts or even a connector. But while you are waiting, hardware delivery, there are many things to do, such as structure analysis, STM vibration test, software analysis using BBMs, or you can also secure the test facilities. And there are many things to do. And after the hardware comes in 4 months, verify those interface compatibility from the, I think you do one by one. When some components arrive, you first check the interface. And there will be significant amount of time needed in troubleshooting. Most likely, your interface, the interface of the component do not match. And you have to, sorry, this is not a lean testing. You learn the testing method. And for the first satellite, EM vibration test will not in one time. Usually, when it is the first satellite, you end up doing a vibration test several times. That's what I have seen in many satellite projects, not only ours, but for other university satellites. So after that one, after you finish EM testings, you can have something called a critical design review. So you confirm that the satellite functions as a system. Everything's integrated, put into the satellite structures, and it works. After that one, 3 months, you wait for the flight model hardware to come. And if you change the design from EM to FM, it may take an unexpected amount of time, even slight changes. Also, there is no guarantee that FM works because EM works. Because the quality controls of the component are not such a good as the other industries. Also, you better do the functional checks of the component one by one when they are delivered. Also, you need to secure the test facility for the FMs. And because the test, there are many things happens, you already have to have a plan B. And 2 months spending FM hardware, and you repair, you may need to repair the FM. And that repair time may be very long. For that one, having EM is very good because you can, at the last minute, you can use EM as a spare. Also, test schedule may change day by day, so you really need to secure the test facility. And for the first 1 month, concentrate on the flight software to find the bug by end-to-end long duration testing. I'll explain about this end-to-end long duration testing. Basically, you check all the operational phases of the satellite. And also, even if you find bugs, you may need to judge whether this bug is actually fixed or not. Because fixing a bug may also introduce another bug. So you be careful. Okay, and project management, project team organizations. Well, usually for university project, it's not possible to have all the talent necessary for the project. Well, because some professor belongs to electrical engineering department, then the professor can find a student who is good at electronics, but it's very difficult to find a student who is very good at structure analysis or making CAD models. So vice versa. So in that case, they need to find solutions to fill the shortage. One, procurement. Another one, collaborate with external people. Number 3, expect students to grow. Actually, yes, students can grow. My first satellite, when I built my first satellite, it was entirely student built satellite. And all of students were from electrical engineering department because that time I was working in the electrical engineering department. And one student was assigned suddenly to make a CAD model, to do structure design. He had nothing to, he had no knowledge of the making CAD working on the CAD model, but eventually he did. And he's now working on the structure engineers in a space company. Oh, yes, student can grow, but sometimes it's risky to expect for student to grow. Also, even if you choose one or two, important things, requirement for procured or outsourced items, they must be made by the team, by the system team. Do not just leave everything to the outsiders. Also, keeping person familiar with the satellite design for operation is important because once satellite is released, already there are the issues, problems, and then you need to find out why we have this anomaly. Then you need a person who knows the satellite design. And in that sense, it's better to finish project life cycles in 3 years from kickoff to operation. Because typically in the university's engineering department, students assigned to the laboratory at the first final year of undergraduate and stays 2 years for the master degree. So it's 3 years. And principal investigators, that is professors or faculty members, that is responsible for keeping student motivations. And also, yes, team needs external assistance. Yes, they have to ask questions. But it's difficult for students to go outside and ask questions because they are scared to go to the to big professors outside. So the principal investigators is responsible for securing communication channels to them. Just writing a simple email saying that my student will contact you about these questions, please help them. Just one single email, good. And the lean philosophy, yes, activities are categorized. Any activities are categorized into 3 types. You can think of your daily life. Okay, what you did yesterday. Think about value-adding activities. That one is to improve satellite reliabilities or enhance attitude control accuracies or others. For your daily life, if you're from universities, reading a textbook and studying such things. 2 non-value added but necessary activities, such as safety compliance, frequency license, Space Activity Act, and others. For your daily life, yes, definitely it's eating and going to bathrooms and take a shower and those things. And now, so it's a pure waste, it's a muda. So it's like searching for tools or other things. For your daily life, you can categorize yourself. So important things is eliminate this waste and do this non-value added but necessary activity efficiently. That's called the lean philosophies. I didn't invent these ones. Originally, this comes from the Toyota production system, Toyota automobile company. They have a very efficient production line, or they are building a production line based on this philosophy. So in the satellite project, there are many ways in the movings and waiting. For example, movings means if the students are scattered all over the campus, to have just one meeting, they just have to walk 10 minutes to the meeting place. Then if you have the 10 persons, 100 minutes. Or you may say that yes, while we're walking, we are thinking about the project. Yes, that may be true, but I think most of the case, you are looking at a smartphone and checking SNS. And waiting, one example is sending email and waiting for the reply. So the time while you are waiting for the reply, nothing progress. So it's purely waste if you are sitting in the same rooms, sending emails to ask some things to a person sitting in front of you. You can just ask. So having the office, the workrooms, the testing rooms, and the ground stations in one building, it's recommended. I'll show you examples later in the facility. Okay, frequency coordinations and licensing. These may result in a change of satellite designs and change of satellite missions, delay satellite delivery. In the worst case, give up satellite missions or limits on the satellite operations and other things. And this kind of work often concentrate on specific members. For example, if it is amateur radio satellite, usually this work concentrated on one person who has a long, who is a hobbyist of amateur radio or something. But multiple members need to monitor the progress. You have to understand human nature. If you assign this work entirely to one specific member, then humans do not work until the deadline approaches. You understand that if you're a student, if you remember your student times, exam is coming on Friday, but you do nothing until Thursday. And on Thursday, you start studying for the exam, but suddenly you start cleaning up your desk and try to avoid start working. So something like that. Yeah. And compliance with safety requirement. This is also important. So non-compliance with safety requirement that may lead to very serious delay of the schedules. So in the worst case, the satellite is not launched. Dummy mass will go instead of your satellite. This is a very scary photo. This really the dummy mass which went to the space. And that really happens. And so if you do not comply with the safety requirement. So to avoid this kind of the tragedy, at the end of conceptual design and detailed design, you list up issues related to safety requirement and confirm with the launch provider so that no mistakes happens. And agree with the launch provider on the safety requirement, how to verify. And you have to agree on a minimum effort. The method can be done with minimum effort. So because safety verification is necessary thing, but it's non-value adding activities. So if you have a time to spend in such one, do more value adding activities such as mission assurance. I am not saying safety verification is not necessary. It is necessary. However, if you finish those necessary things, do more on value adding things. And documentations, so why we need to document? Regulatory work, yes, definitely. Communication within project, yes. Traceability to prepare for the anomalies during the operations, and knowledge transfer, and sharing knowledge with others, and source data to write journals or papers. And this BCD, these 3 points are important for mission assurance. And also, it's important to reflect these lessons learned to the next project. But we need to understand students do not like documentations, to write a document. I'm surprised if we find if I find a student who like writing a document, or if such a student I find, I may recommend the students to go to some literature department or something. But So it's very rare to find a student who like to. So one idea is to link with the student bachelor or master's thesis because they have to write it anyway. And if you're a professor, you make sure that the student do not graduate until he or she write a very good thesis. Yes. And in the mission definition phase, yes, feasibility is important. So to check the feasibility, you need to know the limits of yourself, your teams, yes, not yourself, yes. Team talents and skills, also the budget. Also, this is to the student. You have to understand that professor is not a god. So professor seems like he or she knows everything, but professors are very good at pretending that I know everything. But in fact, it's not. Yes. That means professor doesn't know everything to judge the mission feasibilities. So the professor must be open-minded to suggestions, comment, assistance by the others. Yes. So students do not trust blindly a professor. Okay, it's very important. Yes. So for the feasibility things, if for the first satellite, some missions require 3-axis stabilizations or pointings, it's proposed. If I were the external reviewer, I strongly recommend not to choose that mission because it's very difficult for the first satellite. Also, high-speed communication by mechanical student. I would say in a review that can you do that? Do you understand the communications? So yes, there are things you can do, things you cannot do. So it's not a shame to acknowledge. It's brave to acknowledge. And so by acknowledging that the limit and choose the right mission. Also, mission success criteria is very good indices while you are doing the project. So you set up the 3 minimum success, things to be achieved even if satellite has problem, and full success, things to be achieved when the satellite works as expected, and extra success, something more than expected in addition to the full success. So I suggest to use the quantitative indicator as much as possible, especially for minimum and full success. Like the take image, capture the image of the Earth, at least 1 image, and downlink to the ground station, something like that. Or achieve 100 kbps communications, at least once or something. So you may need to change this criteria as the project proceeds because you may find out that it's not possible. But you have to examine whether the meaning of the entire project can be achieved. That means, can we satisfy the project stakeholders? Because there are always stakeholders. Or can you satisfy by changing this mission success, minimum success criteria? And also, when you discuss design change, examine whether the minimum success can be achieved or not. Because based on that one, yes, the discussion becomes very clear. Also, during the operations, try to achieve the minimum success criteria as soon as the satellite is deployed into orbit. Do not wait. Do not wait that do not wait for a long time. Because satellite may go long anytime. So for the mission scenarios or concept operations, you consider each mission scenario, something it's called concept of operations. Commanding from the ground station, functional flow inside the satellite, and downlink to the ground station. These are all the flow of these 3. Thinking of this mission scenario is very useful for further analysis and derivation of design requirement. So some things, by understanding this flow, you understand that what is necessary, what interface is also necessary. And you make a budget tables in terms of communications, power, and attitude. And these budget tables should be revised as the project goes on and you need to improve accuracy. But if that mission has no margins at the mission definitions phase, from the beginnings, if the margin is very slim, margin is very small, that mission is not possible. For the communications, if the link budget has only 1 dB margins at this stage, I think it's not feasible. For the power, if the power is also true. And the requirement management, you better check the consistency between the mission requirement and the design requirement. And design should satisfy the mission requirement. And no design requirement that doesn't fit to the mission requirement should be included. This is one example. This is a heavy lessons we learned at the Kyutech. So you can see we have this patch antenna. This is the patch antenna. We thought that this patch antenna is good because no need for the antenna deployment. So it's very reliable. And because it's very rare one CubeSat carries a patch antenna. So if we succeed, we can write the journal papers. That's what we thought. Actually, I thought, yes. And I didn't have a proper knowledge of communications that to judge. And I had some external collaborators who developed this antenna. So I trusted blindly. Well, actually, yes, prototype worked fine. Yes, the final flight model didn't work. But anyway, it's wrong to put this experimental the patch antenna. Although I tried to save all the satellite, but this was an educational satellite. The mission was education. For the education purpose, I should have focused more on making design robust so that it can work in space so that we can operate the satellite. Oh, external reviewer could have identified that this risk of this patch antenna, also inconsistency in the requirement. Oh, that's why, yes, professor is not good. Yes, also the professor must be open-minded to external suggestion. And in the conceptual design phase, you have to make this verification plan. So you shouldn't use a design that cannot be verified. You must have a doable verification plan. So these are the test items which is needed for EMs and FMs. This is the case for the ISS reduced CubeSat. This is based on our experience. Yes. In a detailed design phase, you have to select parts and components. Yes, there are many vendors on the internet, but selection must be made carefully. Do not decide by price and performance only. Sometimes availabilities, easiness of handling, or good response to repairs are more important than size, price, functionality. Also, if you develop one component, for the second and third satellite, it's better to use the same designs, if it works, if the first one works. Because to minimize the development work, because slight change may lead to cost increase or longer delivery time. And if you develop the component jointly with some vendor, eventually you should aim at transferring all the know-how to the vendor, because university cannot maintains all the know-hows of the hardware. So in the risk management, FTA, FMEA, and you do risk management, and but you try to minimize the risk based on priority. That's a lean satellite philosophy. You do not tackle all the risks, but you prioritize. Yes. To list up risk with high priorities, external review is very effective. Yes. I ask somebody who experienced a project before. And also FTA, FMEA are not really taught in schools. I teach FTA, FMEA in my school because I have a lecture of systems engineering, but many universities do not have such a courses. So it's better to start from a level student professors can understand, and listing up single point of failures and prioritize studies. And when you list up risk, it's not only part or component, but also work, something like long command or long assembly and others. And in detailed design phase, one suggestion is you make a satellite diehard. Okay, avoid complete failure, such as loss of communication with the ground. In Japanese university, we often use this God PIC. It's a microcontroller, PIC 16877 for power effect. And battery recharging from empty conditions should be verified. Actually, this one helped really save one of our satellite. And you make sure satellite work without battery using solar panel only. And if volume is available, it's better to have a redundant communication link. And power budget must be feasible for minimum functions, even if you lose the attitude controls, or you fail to deploy solar panels, or even if you lose one solar panel. This is one example. Okay, this is one CubeSat. One side is occupied by the camera and antenna. So we have only 5 solar panels. And if you lose one solar panel, that means 80%, 20% power loss. So you have to operate at 80%. And your power budget must be good so that you can do some missions even with 80% capacity. Otherwise, you have 5 single point of failure. You have 5 solar panels. If one of them fails, that's it. And many CubeSat use power reset, but you have to verify satellite can recover from power reset, because sometimes we have the zombie satellite. Because of some leakage current to the microcontrollers, you cannot really shut off the power, and you cannot reset. That really happens. So you verify that the satellite can recover. I think I can skip this one. And for easy operations, imagine how to execute the missions, and you reflect lessons learned from the previous operations. And store command is very useful. Yes. And also, uplink command must be as simple as possible, because small number of bytes to improve uplink success rate. If you try to send the uplink command made of 48 bytes compared to the uplink command made of 8 bytes, success rate is much different. And ground software, it's better to have a ground station software can do the automatic operations. Yes. Also, housekeeping data histories should be kept before if you have a power reset. Also, these important parameters, such as control gain of attitude controls, should be kept. Otherwise, you have to restart all of the attitude controls operation. And reduce easy to assemble and integration testings. So reduce the number of fasteners as much as possible. And implement mitigation against mistakes. So that's one example. This is front side, back side. We have a connector at the front side. This is the Kyutech experience. Every time we make a student, we make a satellite, student makes a mistake. This front and back side. Yes, no matter what we do, but we can minimize that mistake. And one solution is yes, we have this shape at the edge. And when you look at satellite, if you see this edge at the right side, it is front or something. Very, very simple. So being careful is not a solution. Yes, you have to have some physical system to avoid the mistake. And connector, yes, you better save the connector. That means if you do frequent the attach removal, it may damage connector, especially PC104 connectors. It's extremely hard to detach. Yeah. Every time you detach, you put some stress to the connector. And this antenna deployment, you may want to have some physical inhibit, because sometimes the antenna deployment may not be allowed after the final vibration test. That's the case for the KiboCUBE. Yes. And but you may want to work on the software. Then, if you have some physical inhibit, you can work on the software until the last minute. Yes. Because usually antenna deployment is automatic. If you activate a satellite, antenna may be deployed at 30 minutes later. But by having this inhibit, yes, you can avoid that one. So you can activate a satellite and work. Yes. And but make sure that you remove that physical inhibit before you deliver. Otherwise, antenna is not deployed. I think I can skip. Yes, in-house versus outsourcing. So the purpose of an educational satellite is a practice systems engineering and project management. That's what I believe. It's not acquiring handyman skills. It's not to learn how to solder or how to draw CAD models or how to design electronic circuit. If that's a purpose, there are other educational opportunities much cheaper, much easier than satellite. So after all, making satellite from education point of view, it's a systems engineering and project management. So this is to the professors. So do not think that my suggestion not to think that we are teaching students that are handcraft. We are teaching students how to think in a project, how to think in system engineering. Also, better not to try save money by making in-house. After all, it may end up in schedule delay and cost increase. So you can buy quality and time with money. So some students have very good hand skills. Because I have very poor hand skills, I sometimes admire students who have very good hand skills. And but some students are as bad as my hand skills. So relying on student hand skills is very risky. Yeah. So another one. So the safety requirement. This verification safety requirement in FM stage is very critical to pass the safety review. I think this really applies to KiboCUBE. Yes. As, when you make a final product, yes, you really have to be careful to follow all the verifications method you promise to JAXA in safety review. So this one agree on safety hazard control method before FM assemblies between launchers and satellite. For KiboCUBE case, it's JAXA and you. And then this hazard control method must be verified. And that is make sure that it is implemented according to the agreement. So before moving to FM assembly, the team member, especially those who are making satellite, should be aware of what procedure they have to follow and what document they need to make. Because usually safety persons and AIT persons are separated, and safety person says, I told you to measure this one. But this AIT person says, that's not what I was told. And before you fight, you can fight before you can fight with your team, but you shouldn't show that to outside. And good communication between safety officers and AI team is necessary. So in the testing phase, yes, some are in recordings of the on-demand lecture. So you can look at. And this EMC testing is important because especially the uplink. Especially uplink is important. I think I should. Yes, I should explain this one. Yes, if you want to verify the link budget. So in the link budget, from ground stations, and it is amplified antenna, but in free space, it is decayed too much. It is amplified a little bit and goes to loss. So this is the signal levels the satellite receives. And there is a noise level, background noise. And there is this is the signal to noise ratio required to really receive the signal, to decode that uplink. And this signal level you just actually receive must be more than this sensitivity requirement. This difference is called link margin. Problem of CubeSat is this noise levels. Noise levels you cannot calculate because CubeSat is so tightly packed and all of the PCBs are next to each other. So noise coupling is very efficient. And so you can regard just a CubeSat as just one single component. They can couple each other. And then it's very difficult to measure this noise level. So what you need is that you have to measure this sensitivity. And by measuring this sensitivity, and then you confirm this signal level is more than this sensitivity. So this, I think only the measurement can be done. Yes, and you can measure this one by simply connecting cable and varying output from the signal generators and until you find a threshold. So that's for the link budget confirmations. Yes, that's one very important thing, especially for the uplink. And for the end-to-end long-term operation is finding and fixing bugs of flight software. And you do all the operation rehearsals, all the critical mode, nominal mode, and all the mission mode. Yes, those things. How long you do before the deliveries, it really affects your mission success. So you have to allocate significant amount of time to this. Yes. This is thermal vacuum test. Well, thermal vacuum test is thermal vacuum test. So size doesn't matter. No matter this big satellite, this small satellite, it's the same. What do we do the same? But for the temperature conditions, you have to define high and low temperature conditions. You can use flight data of a similar satellite flown in the same orbit. Especially for KiboCUBE, many CubeSat already flown in ISS orbit. And the CubeSat is more or less the same because 5 or 6 surfaces are covered by solar panel. And then you can check those flight data. Many CubeSat already collected flight temperature data. For one example is here. You can get for free, yes. And you better use for high temperature, use high beta angle data, yes. So it's because it is more accurate than thermal analysis. Okay. So when you evaluate the test result, you need to check the consistency of the test result. So pass-fail criteria should be established before the test. And if something which is hard to understand occurs randomly, I think it occurs, yes, many times. Record observation. And don't be optimistic. So you need to fight against normalcy bias. Don't think perhaps it won't happen in orbit, or it was just a random noise, or we just saw illusions, or let's forget about it. For many projects did this one and failed. Also, another note is especially for the radio test, RF equipment is a bit special, and especially for the mechanical engineering student, it's the first time to use spectrum analyzers and those things. And so often they use in the wrong way. And for how to set up test equipment must be checked by multiple persons. I think it's now 10 minutes past. I think I can answer. Okay, I'll go to conclusions. So the mission assurance handbook for university-based beam satellite was published in 2022, and we summarize a point to be kept in mind by faculty members and students to improve the mission success rate. And many of them apply to non-Japanese universities and new space companies. The handbook is open to comment, and it's better to be reviewed globally, and comment will be reflected in the next version. So now I stop here and answer some of the questions. Yes, and
thank you very much, Professor Cho, for the very detailed presentation. Just to let everyone know, this presentation is already on our website. My colleague Wenbin has been sharing the link in the chat. So if you want to take a further look at this presentation, please go to our website. And Professor Cho also has pointed out that a lot of the topics are linked to the different past activities that we've done through KiboCUBE Academy. There are pre-recorded on-demand lectures that are related to this one, and he also organized that in one of his slides. So please take a look at that, and yeah, make sure to look at our website as well. Also, I'd like to just to mention there were many comments that the handbook was not accessible, maybe because it's fantastic that we have more than 100 people here, but maybe because all the 100 people went to the link at the same time, there was some issues there. So for some people, it seems that, yeah, the UNISEC handbook link did not work. The link is correct. So maybe if you can try to connect again later in the day or later in the week, it will be accessible. As of now, yes, I've confirmed that it doesn't work. My colleague Wenbin has made a different link so that it's accessible for now, but the link is right. So when you want to refer to it later in the week or later in the day, please use Professor Cho's presentation link. But yeah, UNISEC will try to figure it out so we can have it back online. Yeah, with that, I'd like to go on to the Q&A session. If you have any questions, please throw them in the Q&A box. I only see one or two questions, so I'll start with them. One was probably talking about page 31. So this person was asking about the dummy mass. I think the lesson was more about if your project is not on time, instead of your project, a dummy mass will be launched. But the question was, what will happen to the dummy mass if it's put up in space?
Where is the question? I can, is that in the chat box or Q&A?
It's in the Q&A. So he wanted to learn more about the dummy mass. So here in this page, it says, in the worst case, the dummy mass will go instead of your satellite. This person wanted to know if the dummy mass is put into space and what happens.
Okay. I can see. I see Q&A in already answered.
No, it's in open. It's 1:44 p.m.
1:44 p.m.
1:44 p.m.
Okay. Now, can you explain more about dummy mass? Does it make to go and run return trip in the launcher, or is it put at any moment in the space? Well, I think this dummy mass is attached to the rocket body. It will be never separated, because if it is separated, it becomes space debris. So it will be attached to the rocket. The dummy mass is necessary because rocket other satellites. You can see the three satellites. Actually, one is our satellite. So the other three satellites were already put, and if we do not put anything in this dummy mass point, there's some misalignment in the center of gravity. Then it may not be good for the launch of the rocket. Then to balance the center of gravity, they put this dummy mass. And for during the flight, this dummy mass is put just to keep the mass balance. So after other satellites are released, no need to release this dummy mass. So it will stay with the rocket body. So this dummy mass is actually bolted to the rocket and go down to the atmosphere with the rocket. Yes. Did I answer the question?
Thank you, Professor Cho. I think that was very clear. The second question was, is the Lean handbook for school level? So I believe this is for university level. I guess, yeah, it's not for high school level. It's really for university bachelors.
Yeah.
Okay. Another question was about the frequency. So for frequency issues, we do have other lectures that, of course, mention ITU. We cannot talk about frequency without the links between the International Telecommunications Union. For KiboCUBE itself, UNOOSA has also a guidebook together that we organized with ITU about frequency allocation. So maybe it was not specifically mentioned in this lecture, but of course we respect and we work with ITU on these matters for frequency allocation.
Yeah. Yes, I think you answered correctly. Yes.
The next question is, what would be the cost of a CubeSat project, including a few training sessions? I think this is for Kyutech. So if there's anyone interested in working directly with Kyutech, I would advise them to go to the Kyutech website and contact Kyutech directly, as I believe I guess there's costs and there's different forms of partnerships.
Yes.
We can move on to the next part of today's webinar, which is the actual satellite facility tour of Kyutech.
Okay, so next one, satellite facility tour. Yes. Okay. I can skip all the introduction. Yes. So what we do is because we are very far from you. Yes, 10,000 kilometers from you. We cannot bring you to our facilities in person. Well, you can come, yes, if you want. Yes, you are very welcome to be facility. However, thanks to the modern technologies, we can take you to a virtual tours. So what we do is, I have some recorded video. So I go through and stop one by one and explain what are these. And if you have a questions, yes, you can ask there. Yes, and so I'll answer that one later. Okay. So I'll show you first Kyutech satellites, ground stations, and antenna. This belongs to the one buildings. Another one, 4 to 10 belongs to other building. The picture you see here is all the testing centers, which show the vibration machine, shock machine, and those things. So first, I'll show you these buildings. These buildings actually, when I should have put the pictures of the current status, but when we took these pictures, antenna is not there. But right now we have so many antennas on top of the rooftop. Yes. So we are staying in these buildings. Actually, our office, some laboratory occupies these 4 floors. Yes, I stay. My office is here on this 4th floor, and the ground stations is 8th floor, and antenna is on the rooftop. This buildings is the highest. This is sittings on a hill, small hills, and this rooftop is a kind of highest around this area because we are located in some residential area. So surroundings is at most the apartment. So not much of high rise buildings. If we go to the very the center of the town, yes, there are lots of the taller buildings, but at this point, it's a kind of residential area. So we have a quite good view from the rooftop. Yes. Okay, and so first, I'll show you the satellite we have built by the satellite models. So this is from left to right. We have a BARS 1, BARS 2, BARS 3, BARS 4 satellite. You can see. Okay, let's go back. You can see how the models become so sophisticated. For the first satellite, actually, the first satellite actually look like yes models, but this BARS 4 satellite model, it looks really real. Yes. So actually, students took the group photo with these satellite models. And it really looked like also because they took the pictures in a clean rooms, it really looked like they took with a real satellite. But no, it's not. It is just a model. Anyway, so these are the how the satellite evolved from BARS 1 to 4, and we don't have BARS 5. Oh, okay. No, we don't have BARS 5 here, but yes, BARS 1, 2, 3, 4. And these exhibition areas, if you go inside buildings in the 4th floor, when you exit the elevator, we have this exhibitions area. So we have those the satellite. Yes. And these are the other satellite. These three satellites. This is our Velox 4. This is Spashing 1. This is our Velox 3. These are the CubeSat and made jointly with Singapore. We have a strong collaborations with Nanyang Technological University. This our Velox 3. This you can see this square hole. This is a pulse plasma thruster. Yes, Singapore contributed this 1U site, and they just brought pulse plasma thrusters, which has a 1U volume. Kyutech provided satellite bus, yes, which is made of 1U CubeSat. And this Albo Velox 4 is the second of these ones. You can see a very nice wing. And this one also carried the pulse plasma thrusters and also camera. And we succeeded in taking nice pictures of the Earth. However, pulse plasma thrusters, we could operate. However, every time we fired pulse plasma thrusters, some things in satellite malfunctions. So it has too much noise. This Passion one, it's very interesting. You don't see much of the menu of the red satellite. Yes. The reason why we have red satellite is, in thermal controls wise, red had the good thermal property. That was official, but unofficially, just simply project managers like the red color. So yes, so we chose the red color. And this is a Kitsune satellite. This is 6U CubeSat, and we have this different lens. So it has a 300 millimeter focal lens. So this one carries the 4K cameras, and can capture the image of we try to capture the image of 5-meter resolution. So far, we have achieved 9-meter resolution. So now you are in a ground station on an S4. So using these ones, yes, we operate one times. We operate how many satellites? 5 or 6 satellites using these ones. These stations is an operation for the Kitsune. Yes, we are operating. This is a non-amateur band, and this one is the stations we use the S-band dish antenna. Yes, and we have one amateur stations which we operate undergrad student satellite, and another satellite. This one operates UHF, VHF. Sorry. And this part, we operate about satellite. Yes. So we have how many? We have 5 UHF antenna, 5 Yagi antennas, and 1 S-band dish antennas. So when we have the operations, students come to these rooms, and yes, they operate. And point is that point I want to make is that we are located here. Yes, and some students have an office here, and we have 8 floors, ground stations, and we can just move up to the ground stations by elevator, and so that the environment is very cozy. We don't have to go outside. And that is very useful when we operate in nighttime, during the midnight. Because many of our satellites is ISS orbit. That means time is not fixed. So sometimes it's early morning, sometimes very late evenings, and basically it's 24 hours. So it's better to have the ground stations in the same buildings as the office, so that when they are not operating, they can stay in the office, or simply they can go home. Yes. So this is antenna. We have a 3 antenna here. This is a UHF VHF antenna. This is a UHF antenna, and this is another UHF antenna. So we have this lightning rod, and ground stations is located just below this one, just below this one. And so that we can have the minimum length of the RF cables. Because the signals decays in RF cables, so you want to minimize the cable length to the ground station as much as possible. Actually, we have a 4th antenna, so you can just, you see there's only the basis here. But yes, we have a four antennas. And also one thing I want to mention is that this antenna has an elevator, which is a manual elevator. And because we are on the top of the roof, and we are located in the west side of Japan, and we have a typhoon many times, especially due to global warming. So we have a lot of typhoon recently, and some are very big. And whenever typhoon hits, we have to maintain, we have to fix the antenna. And to climb up this antenna tower is very dangerous. So we cannot let a student do this one. And does that mean I have to go up? No, I'm also scared. So we always ask the company to come and to do the service. And that's sometimes it's too much over financially. So this is the newest antenna. When we built, we made this manual elevator. So when the typhoon comes, we can lower this one by rotating some handles. And also by lowering, we can access while standing on here. And so there are some bases here. So even a student can access to this one. So when you build a ground station, you better think of this one, especially if you are located in an area where lots of typhoon or hurricane comes. So this is the S1 ground stations. Yeah, we just rotate just for this. This is the 2.4 meter dish antenna for S-band and C-band. Yes, we are operating. Yes. You can see there are not much of a high building around here. And yes, so it's good. Here, we have some structures on the rooftop. And especially one thing, because this is the highest around this area, there are lots of the cell phone towers. And so sometimes it gives some interference. Okay, and we go to the next buildings. So this building is a test facility and clean room. Actually, this building is located around here, next to this building. So to go to these buildings, we have some back door of the main buildings, and by opening the back door, if you run, I think in 5 seconds you can reach. So even if it is raining, you can just run. Yes, but with satellite you never run. Okay. Actually, satellite stays in here. The satellite goes to this buildings. We have an anechoic chamber here. You can see these 2 walls. This is the place we have anechoic chamber. So when we do the anechoic chamber test, satellite comes to here. But otherwise, satellite always stay within this building. Okay. And inside this building, this is the first floor. Okay. So I'll show you the entire view of the first floor. This is shock machine. Okay. So this is a nice, compound, and this is a vibration shaker. I will explain more in detail later. So this is a vibration shakers. This is the shock machine. Yes, we cover this ones by the curtains so that we can do the flight model testing as well. We have a vacuum chamber. Students are doing some thermal vacuum test, and you can see the big thermal vacuum chamber here. In upstairs, we have the ready room. I'll show you the video later. So that one is a small vacuum chambers. This one is a big vacuum chambers. Inside with 1.5 meter width, 1.5 meter diameter. So we have a small vacuum chamber, another one, and also we have a thermal side. So these are the overview, and I'll explain one by one. Okay. Yes. So this is a vibration shaker. So these shakers vibrate in this state, vibrate in up and down. And we have these horizontal tables, and when so we can put the satellite on top of this one, or we can rotate this head 90 degrees attached to this table and shake it. But the satellite is shaked in a lateral. This one is all of the so-called, this is the amplifier. So we have the all the accelerometers attached to the satellite, and that signal is the amplifier here and connected to the PC to capture all of the signal. This one is a shock machines. Yes. Here, this cylinder is a high pressure air. And using this high pressure air, we shoot some projectile through this through the Okay, we shoot projectile and hit these tables. So we put the satellite on these very thick tables. We hit this bottom of these tables by some projectiles accelerated by the air gun. So, and to simulate a shock generated by pyro device on board the rocket. It is necessary when you do the rocket launch. For the ISS case, no need. This is a thermal vacuum chamber. This was made by a student from Ghana. He got a doctorate degree making this chamber. This vacuum chamber is for the thermal vacuum. And it has to cool the satellite. It uses a pellet device, which we can cool a satellite by electronically. Because we consider if the student goes back to Africa, it may be difficult to get liquid nitrogen supply constantly. Usually, a thermal vacuum chamber to achieve cryogenic temperatures, we use liquid nitrogen. However, liquid nitrogen supply is difficult. But in Africa, the students say that we have electricity and water. Then we can use electricity to cool down and water to cool down further. And we bought this chamber. This is second-hand chamber. For, I think, almost free. I think some company gave us because they are about to throw away. We paid, if we paid, I think we paid only $2,000 or $3,000, several $1,000. Yeah. And student built, so the chamber came separately, in a separate component, and the student built by himself. It was a very good exercise. So it can reach to minus 70 degrees. And it's not good for geosynchronous orbit, but it's good for the ISS orbit. Because in ISS orbit, the temperature doesn't go down much. Yes, because it's in a lower orbit. Because the Earth is very near. Also, you have an eclipse. So that's why this is good for the for CubeSat in an ISS orbit. This is another thermal vacuum chamber. This one we use liquid nitrogen. So this silver metallic pipe is bringing liquid nitrogen, and using evaporation heat of the liquid nitrogen, we can cool down. Yes. This is good for also good for the CubeSat. This is a very big chamber, 1.5 meters, 1.5 meter radius. So we can put a 50 centimeter class satellite. You know, vibration test other industry use, such as automobile or electronics. But the thermal vacuums only space industry uses. So for vibration shakers in Japan, the satellite developer can go to some testing centers, which is offering testing service for other industry. But for this kind of thermal vacuums, it's very unique. So the place is very limited. This 1.5 meter diameter vacuum chambers is the biggest as a university. If you want to test something bigger than this one, you have to go to the JAXA or some space company. So you have these feed throughs. Through this feed throughs, we connect with a satellite inside. Yes. So lots of cable going. Yes. And this one's, this is the liquid nitrogen, right? Yes. And this is not a refrigerator. This is a thermal cycle chamber. So this internally, this is 50 centimeter. So we can put the entire CubeSat here. And this one, this cannot make to the vacuum, but this is easy to make high temperature and low temperatures. And control is very easy. We just set the time temperatures and push the button. That's it. And thermal vacuum chambers, it's so difficult. So this is the ready rooms. So this is the rooms when you climb up. So if you go up these stairs and if you enter these rooms, you go to these rooms. Yes, these rooms is ready rooms, waiting rooms, because for thermal vacuum test, once you inject the liquid nitrogen, you cannot stop. If you stop, your satellite gets too cold. So you can't stop. So it's 24 hours. Usually, even for CubeSat, it takes 2 or 3 days. So you have to stay overnight. And staying overnight on the first floor is not really good. And so to stay in some a little bit more cozy environment, we have this one. So because we open this facility to outside users, so people will come and usually they stay in here at the office, as a temporary office. So if you go through this door, yes, it goes to the testing center. So this is the clean rooms. We have 2 of these clean rooms. Yes, these clean rooms, I think it's ISO class 8. That's the lowest class of the clean room. Actually, we they converted regular office to the clean rooms and change the floor and change the ceilings and put some air conditioners and also air filters. And yes, it took around how much? $100,000. Yes. Yes. It's much cheaper than building from scratch. We have a radios and we have also a shielding box. We can put a satellite inside and we can emit a radio in here. Because initially it was an office, also some laboratories. We have this this thing. Usually, when you build a clean rooms, you don't have a sink. We have 2 of the clean rooms in the 2nd floor and the 3rd floor. 2nd floor, I think this was which one? I think this is the 2nd floor. This 2nd floor's clean room is used for the external users. And the 3rd floor, we have the same clean rooms that's used for the Kyutech satellite project. So we go into the bathrooms. So we enter the room. So here are the clean rooms for our own satellite project, like a bird satellite. Yes, and student rooms are 1, 2, 3. These are the rooms for the student who work, and there's no door. We remove the doors, and we put a door for the security at the front side. But inside, no door, so that it becomes very transparent to everybody. So this is a clean rooms for our own project. So yes, there are lots of equipment and also the satellite and also some cages, which we I think this is for the magnetic field calibration. There's some students working here. Yes, I think he's working on some EPS or something. Yeah, some satellite, which students are really working on this one. Yes. This is a EM, this is I think a FM, for that covered by the laptop. Now I show you the office of a student. Sorry. This we call the bathrooms. It's I think they need to clean up a little bit. Yes. Now it's used for another project called Leopard. So we call it Leopard rooms. And usually students stay here. You for only one student. And however, the student usually stay here, and when there is no class, they come here and stay and work. And also in the center tables, they work on satellite hardware. So usually, when we have a project, we put all the team member here for about 1 year, and so they interact each other in one room. So as you can see, we have the office, laboratories, also testing facility, clean rooms in one buildings. And the next buildings in a 5-second round, we have the ground stations. So in this way, we can so tightly packed, and we can reduce all of the waste in the movings. And also by putting everybody here, I hope they can communicate without without using any emails. But a student use Slack. Yes. Oh, okay. Yeah. Okay, I think that's it. Yes.
Okay, thank you very much, Professor Cho, for this interesting laboratory tour. It's really nice to see the actual facilities that are being used for satellite development. So I would like to pick up first the questions related to this session, and then maybe if we have time, we can pick up some of the questions that came from the session before. So one question that came for this session is about the vibration shaker test facility. It was asking which level the clean room is. I believe there's ISO clean room standards, and I believe you mentioned it, but can you elaborate again the vibration shaker test facility?
You mean the inside this tent?
Yeah, the question just says, is the vibration shaker test facility in the clean room class 100. No. The comma is actually strange. Yeah, I think this person wants to know the standard.
Well, okay. This clean booth is I think. These clean rooms can provide ISO class 8. There are some level of clean rooms, and ISO from ISO class 1 to 3, 4, 5, 6, and something like that. And ISO class 8 is the lowest levels. It's just a primitive levels. So it is, but for satellite, ISO class 8 is good enough. And
Okay.
For this kind of a temporary tent, yes, I think if we keep it operating the filter for a long time, I think we can still achieve class 8, but not more than that.
Okay, thank you very much. I hope that answered this person's question. Another one related was, do you do any acoustic tests? We didn't see any facilities related to acoustic in the tour.
No, we don't. Acoustic test is required only for big satellite, because for big satellite, it has a large area. Then all the force received by the acoustic force is proportional to the surface area. And acoustic test becomes necessary somewhere around 200 kilograms or 300 kilograms or more. For a satellite of 50 kilogram class or 50 centimeter class, the vibration you receive from the bottom is more than vibration you receive from acoustic. So for the small satellite of the size 50 centimeter or less, you don't need an acoustic.
Okay, thank you very much. I think that's very clear. Another question, I'd like to combine two questions because it's more about partnerships with Kyutech, with the BIRDS program and access to these facilities. So in order to be able to access these facilities and work with Kyutech, what are the ways of partnerships? What are the ways that students can approach Kyutech and you, Professor Cho?
Well, I think one way, we have something called Space Engineering International course. So that's a postgraduate curriculum, official educational curriculums, which offers master or doctor degree. So you can enroll as a full-time student at Kyutech, and you can go through all the hands-on education and get a degree. That's one. Number two, if you are not from some company or organizations and do not really care about those academic degree, we can do the joint collaboration work. And so you can dispatch your engineers to the Kyutech, and we can train the engineers, also test the satellite. And that's something called JCUBE. JCUBE is an initiative between JAXA and UNISEC. So it provides low cost. It's not free as a KiboCUBE, but low cost launch opportunities for the teams made of Japanese universities and a foreign entity. Doesn't have to be universities, foreign entities, and for the capacity building purpose. So we can apply for that one. And so we are already working on that framework with a country like Malaysia or Thailand or Mexico, for those countries. Yes. Or you can simply come for the testings. Facilities opens. You can go to our website, or you can simply email to me. Yes, I can direct to the person who takes care of all the logistics. Or we do have some training programs. The one program is 10 days satellite training, satellite testing tutorials. So we have all the lectures and also hands-on trainings using this facility. So there are various menus. So just simply write me email.
Okay, thank you very much. I think that's very clear. I know Professor Cho's email address was on the Kyutech website. So yeah, have a look and let him know. For the questions, I would like to also go back to some of the questions that came from the first session that we were not able to answer. One question is, what is the, I would say, average cost in time that it takes to gain the certifications for the satellite launching? So there's a lot of certificates and approvals that you need to get within your country. It also depends on which country you're from, because the approval is very different in each country. But let's say in the case of birds, when you launch from Japan, how long does it take for you to get all the approvals and certificates? And does it have a cost for you?
Okay, so you mean the regulatories?
Yeah, regulatory.
That matters. Well, all of the regulatory matters are basically free. So in Japan, two very important regulatories matters. One, frequency. So we have to go through the proper frequency coordinations and also through ITU and also domestic radio license. We have to pay some very small money, like $30 something to get a license. Yes, but basically those are all free. Yes, and for the Space Act, another one is Space Activity Act. For every entity who launch a satellite from Japan, yes, we have to get government approvals. It's also for free. That doesn't cost. But the truth is, for ITU coordinations, for amateur, we do ourselves. But when we use non-amateur frequencies, we often hire consultant. Yes, and consultant depends on how much you do. But I think it's not for it's much cheaper than launch. Yes. And for Space Activity Act, no, we do ourselves. Yes, and for if it is amateur radio satellite, yes, everything we do ourselves. The timeline, Space Activity Act takes maybe several months. Yes, and frequency, that's become a headache right recently. Yes, sometimes it takes longer than building satellite. So takes at least 1 year. So that's why I told that 30 months to build a satellite, but the frequency sometimes takes more than 30 months. Yes.
Thank you very much.
That depends on the country.
Yep, thank you. As Professor Cho said, that was the case for Japan. Of course, it's different in each country, so you would have to find out how it is. Usually there's a government process, and yeah, I would say it would really depend, but especially for the ITU related things, it does take much more than a year. So as soon as you have an idea to put up a satellite, you start your frequency related documents as well. Yeah, I'd just like to pick up maybe 2 more questions and then we can finish. One is, do we have to make an EMC, EMI test for every single component? And are there any other options than EMC, EMI tests to check for EMC, EMI? This is talking about, yeah, the previous session.
Yes. Yes, for EMC, EMI, EMC, I think for the CubeSat, I think I suggest you do as a system because it's very difficult to separate individual component or parts because it's so tightly packed. So once you build entire satellite, I say at the EM stage, and all the systems that get together in the same distance, in the same way it connected each other, you do the EMC test. EMC test is basically, can your satellite live with the noise your satellite itself generates. Don't worry about the noise coming from others, or don't worry about whether your noise affect others, because your satellite is completely turned off before you are released. For no way you make any you annoy somebody else. So think of only yourself. Then also your satellite in a space. So nothing coming from space. So the self-generated noise. Whether you can live with self-generated noise. That's the only thing you need. Yes.
Okay, thank you very much. The last question, I'm going to combine two questions. So one is, how much of the satellite is made out of COTS products, COTS off-the-shelf related products? And the other question was, sorry, my chat froze. Let me, hold on. And yeah, the second question was, how much would it take to build a 2U CubeSat with a camera and radiation sensor? So it could be a ballpark figure, but how much would it be in value USD of assembling and testing a 2U CubeSat with camera and radiation sensor? Of course, this will differ whichever country you're in, and because of the access you have to different products and testing facilities and human resources. But if you have maybe a bit of a ballpark figure.
Okay, and for example, for this this kind of the satellite, the only space grade parts we use is a solar cell and a glue. Glue, you can see those blue, brown things are coming out from a satellite, solar panels. So these are the glue. These are the glues you attach the solar cells. We have to use a space grade because the commercial off-the-shelf glue cannot survive low temperature in space. And so far, we use only the space grade glue and solar cells. All others are made of COTS parts. Yes. Even for this 6U CubeSat, I think everything other than solar cells and glue all made of terrestrial COTS parts. And to build a 2U CubeSat with camera and those things, well, depends. But if you build everything by yourself, buying all the electronics parts at the DigiKey or somewhere, and build further by yourself, I think overall hardware cost, I think, how much? To you. I think if you build yourself, okay, you can overall hardware cost would be $30,000. However, you cannot. Also, you shouldn't. Probably don't work. Okay, and unless you have very good hands. And the key component you better rely on external vendors is a radio. Radio, UHF radio or VHF radios, it is full of analog technologies, analog microwave circuit. I think if the beginners work on that ones, probably it won't work. So at least radio you better buy. So our goal is to make this bus satellite as low as possible. So far, just hardware alone, hardware price alone, we accumulate all the prices for just to when we build a 3 satellite together or 5 satellite together, if we set up all the cost, I think we are now around $30,000. However, we want to make it less than 20, or the good is the 15,000. That's our goal. But yes, for the beginner, if you are really beginner, I really suggest some things to buy or introduce something which have already flight heritage. And well, price may be 2 times or 3 times, but the mission success rate is more than 2 times or 3 times. That's what I recommend for the beginner. If you have all the experience and all the good hands, then you can try to make everything by yourself.
Okay, thank you very much, Professor Choi. I think that was clear. And thank you again for the 2 consecutive sessions. We were able to learn a lot of things, and to everyone, it might have been a lot of information to you, but as I said, the presentations are already online on our UNOOSA website. So please have a look and download it from the website, and also try to access the handbook again. Maybe not today, but on a different day, the Lean Handbook of UNISEC. The access should be better by then. Okay, with this, I'd like to thank you all for joining us today. Please answer our questionnaire before you leave. We would really like to hear your feedback. Regarding KiboCUBE, I'm really happy to say that we will be able to open a new round within this year, so definitely around the summer. So if you are interested in developing a 1U CubeSat, KiboCUBE will be your opportunity. We will be opening a slot for 1U CubeSat to deploy from the International Space Station. And all the things that Professor Cho mentioned and all the things that we are covering in KiboCUBE Academy will be extremely helpful for the application for KiboCUBE. So if you're interested in that, yeah, please stay tuned. Definitely will be opening within this year. So thank you again for all of your participation. And yeah, everyone have a nice day wherever you are. Thank you so much.
Bye.